Okay, we have another integral today. This one's from UNSW 2019, number 5. We have the integral from 0 to infinity, e to the 2x over 1 plus e to the 4x dx. Okay, we can actually do this one pretty quick with a u substitution, but I thought that was a little too maybe straightforward, kind of boring. So in order to make this a little more complicated, what I'm going to do is let's just do it a different way. And I can multiply it by 1, multiplying by e minus 4x over e minus 4x. When I do this, what's going to happen, now we have just multiplying everything in here and here, we end up with e minus 2x over e minus 4x plus 1. But now let me just reverse this, the order in the denominator here. I'm going to write it a little bit of a different way. But really, instead of writing it 1 plus e minus 4x, let's write this as 1 minus e minus 4x. The reason to do this is because what I want to do on it is use the geometric series formula. For the geometric series, for 1 over 1 minus x, we can write this as the sum from n equals 0 to infinity of x to the n. But this only converges when the absolute value of x is less than 1. So here I want to do the same kind of thing where the input on it instead of x is going to be this. Let's just move this over for a second. So now just focusing on this part right here, putting it into this format, I'm saying we're going to have 1 over 1 minus e minus 4x. Then inputting this into this thing, it's going to become the sum from n equals 0 to infinity of minus e minus 4x, just plugging into the x to the n. And now we need the absolute value of all of this stuff to be less than 1. Well, for this piece right here, just notice our bounds are going from 0 to infinity. When technically at 0, this is going to be minus 1, absolute value minus 1 is 1. But we don't really care about actually at the bounds. When you're close to 0, this is going to be fine. And then this is just going to be decreasing. As it goes to infinity, this is going to be rapidly going to 0. So this piece here is going to work fine. Now for this, one thing I can do is I can rewrite it a little bit differently. I can break out the minus sign. I can write this as minus 1 to the n e minus 4, distribute in the n, we can write it as like 4nx from 0 to infinity. So then what I'm going to do is just take all this and plug it back into our integral. So we're going 0 to infinity e minus 2x, plug in the sum. But now let's just distribute this term in here, combining it, we've got the same base here and here. So when I put those two terms together, notice I just factored out a minus 2x to get this 2n plus 1 here, but this is the same thing as multiplying these two together. And then here what I want to do is let's just reverse the order of the integral and the sum. I can do this because we have our absolute convergence that we showed right here. But now from here, this piece right here is just a constant, so I can bring this out front of the integral. And then this is actually just something we can integrate, like this right here is just a constant. So doing all this, what's going to happen, we have our sum, we have our constant that we're going to bring out front. Then integrating this, we're first going to get the whole same thing back, minus 2x, 2n plus 1. But then in the denominator, we're going to get this minus 2, 2n plus 1 popping out, and we just need to evaluate from 0 to infinity. Now when you evaluate this part to infinity, this is definitely going to 0. We don't have to worry about this part. This is always going to be positive because n is starting at 0. So this is always going to be going to 0. We don't worry about that. And then when we plug 0 in here, the numerator is just going to be going, this is all going to become 1, because we're going to end up with basically e to the 0. So cleaning this all up, we're going to have our sum, we'll write it as minus 1 to the n. Now when we evaluate the second part, we get a minus sign, so that's going to basically turn this to a plus, and this is going to become 2n plus 1. And then one last thing here, this 2 is just a constant, so let's write this as like 1/2 in front. And then we're going to have just everything else. Now from here, let's just write out a few terms. We've got the 1/2 in front. You plug a 0 in, the first term's a 1. You plug this 2n plus 1 is always odd, right? You plug 1 in, you're going to have a 3. So it's going to be like minus 1 over 3, plus 1 over 5, minus 1 over 7, on and on forever. But now for this thing right here, you may recognize it. This is a lot like our power series formula for arctan. So here we have our power series for arctan, just noticing like this is really close to this. The only difference is this x to the n here. Well, all we need to do to make this work is if we look at arctan of 1, then this piece goes away, because then if you plug a 1 in for x, this is always 1. So now we have the exact same expression we have down here in our problem. And then for arctan of 1, we know what that is. That's just going to be pi over 4. So then this allows us to just go ahead and say that this right here is going to be pi over 4. Multiplying it together, pi over 4 times 1/2, and I get my final solution of just pi over 8. Okay, there you go. Good problem, UNSW 2019. Thanks everyone for watching. Have a good day.